This slide illustrates a orientation tolerance on just one side of the slot. Okay, so what we have here is we have an extension line coming from one side of the slot, and the perpendicularity tolerance is applied to that one side of the slot. Okay, so that controls only one surface. Okay, let's talk about angularity tolerances. So angularity on surfaces. Tolerance is always referenced to at least one, but it may be more, datum features. The feature control frame is attached to a leader or attached to the extension line, one way or the other. Feature control frame may be attached by leader to a surface in a CAD model. That's the other way to apply it. Okay, so here's what we have. Here's that leader attached to a CAD model. Here is our drawing. We have a datum A. We have a basic dimension that defines the angle of that surface. And then we have the angularity at 9 thousandths. So what does that mean? What does that mean on my part? Okay, that's in this next slide here. Several ways to do that. In this particular case, we're dimensioning that side by its dimension and then a basic dimension on the angle. What does that mean? That means I have a maximum of 260 here. That could be the maximum, and then based on that, I have my 9 thousandths parallel planes that establish the tolerance zone. Now, that's what that means. Okay, so the 30 degree here is perfect. So these two lines here are based on this perfect 30 degree angle, and that's how we dimension, that's how we set up the tolerance zone on an angularity. Okay, here's angularity reference to one datum feature. So the part's constrained in rotation only to the reference datum. Setup remains specified angle relative to the reference datum, and the dial indicator or other measurement device is used to measure that surface orientation. Okay, here's the example. We have a block. We have the 30 degree basic dimension. We have an angularity at 9 thousandths with respect to A. So what we do is we set up a sine bar that gives us exactly 30 degrees. We clamp the part to datum A. Okay, and then look, see, there's no parallelism required, to the two sides, but we'll talk about that in the next slide. And then we run our dial indicator over the surface. As long as our full indicator movement is less than 9 thousandths, the part meets this requirement here. So that's how we would check an angularity to one reference datum. So let's talk about two reference datums. So the part is constrained to both reference datums. The setup maintains the specified angle relative to the reference datum, and the dial indicator measures the orientation variation. So here's a cartoon of how that's done. Okay, so in this case, we have the main datum A, just like in the last example. Main datum A is set up here, and our sine bar simulates datum A, but we also have a datum B simulator here now too. Okay, that's to pick up this datum here, and then we run our dial indicator over the surface. As long as it's less than 9, it's the same. So you compare that two datums with our method for one datum. The only thing is we don't have a simulator for datum B, is what the difference is between the two. Tangent plane. So orientation tolerances may be controlled to a tangent plane. So instead of being controlled by limits of size, the orientation is established from the high points of the surface. And this is how that's done. Okay, so essentially what we're doing here is we put this T modifier in the tolerance. So that's the tangent plane symbol. And what that says is, we got the 30 degrees here. We come over here, we find the high spot, and that high spot dictates the tangent plane. That's what that means. Okay. Combined form and orientation tolerances. Control orientation to one value and form to a smaller value. Orientation also controls form when applied to a surface. And here's an example of that. So really what we're doing here is we're using a orientation tolerance of 12. Okay, that gives us this orientation tolerance of 12. And then once we have that, we're going to establish a flatness of 4. Now if you notice, we're basing this 4 thousandths flatness based on the actual dimensions and the actual high points of the surface, not based upon what datum A is. Okay, so here's our flatness tolerance. Any orientation provided the actual surface is within the perpendicularity zone. Okay, so here's the perpendicularity zone. As long as the surface is within the perpendicularity zone, within this 4 thousandths flatness tolerance, the part is good. This concludes our movies for Chapter 7.